Hi everyone, in this video we solve problem 3.14 from the book Applied Thermodynamics, McConkey and Eastop. Here is statement of the problem 14 from the chapter 3. A refrigerant is compressed reversibly in a cylinder according to a polytropic law from 2.62 bar dry saturated to 8.2 bar when the temperature is then 40 centigrade. Using the refrigerant property given in the table 3.2, this is the table 3.2, calculate the polytropic index, the work input during the compression process, the heat transfer to or from the cylinder wall during the process. The refrigerant that is compressed, its initial conditions pressure is P1, that is 2.62 bar. Also it's initially the refrigerant is dry saturated at this pressure. Then the final conditions after compression, the pressure P2 is 8.2 bar and the final temperature T2, that is 40 centigrade. Also this refrigerant is then in superheated region. What we need to calculate polytropic index and work input during this compression is required, and the heat value that either it is rejected or transferred to the wall of the cylinder. Let me draw its pH diagram. Initially, as it said, the refrigerant is dry saturated, then it is compressed and reached to the pressure P2. This is the pressure P2 value. Here the pressure, it was initially P1 and the condition of the steam was dry saturated. That's why it touched the dry saturated curve line. This is condition. This is state point 1, then this is state point 2. The steam is then compressed. Work input will require and reaches to state point 2. Similarly, its enthalpy change from H1 to H2. Now come toward its solution. At pressure P1 2.62 bar and dry saturated condition, the specific volume value V1 is equal to this Vg value, and here you can see from the steam table that is 0.0757 meter cube per kg. Also the specific enthalpy H1 value that is equal to Hg, and it is 2929 kilojoule per kg, and it is 292.9 kilojoule per kg. Similarly, the refrigerant conditions at the final state at pressure P2, that is 8.2 bar, and temperatures T2, that is 40 centigrade. Here you can see from the superheated value of the steam table, the specific volume V2 value is equal to 0.02615 meter cube per kg, and the specific enthalpy H2 value is 322.6 kilojoule per kg. Now we will find the N value, as we know that during polytropic compressions P2 divided by P1 is equal to V1 divided by V2 to the power N. Now just simply put the values of P2, P1, V1, V2. P2 is 8.2 divided by P1, that is 2.62. V1 value is 0.0757. V2 value is 0.02615. Solve this on calculators and it will give you the values of 3.13, and similarly when you divide this on calculators, you will get value that is 2.894 power N. Now apply ln to the both side. It is the simple log rule that it can shift the exponent to its coefficient. So I can also write like this, ln. So here this is n, then ln 2.894. Now divide both sides with ln 2.894. This will cancel out and it will give you n equal to ln 3.13 divided by ln 2.894. Let me solve this on calculators. That will give you the value of n. And the value of n is 1.073. This was our first requirement in the statement. Next we need to find the work input value that is required, that is equal to P2 V2 minus P1 V1 divided by n minus 1. What is P2 value? That is 8.2 bar, multiply with 10 to the power 5 to convert into Newton per meter square. V2 value is 0.02615 minus 2.62 multiply 10 to the power 5 multiply with volume value V1 value, that is 0.0757 divided by n minus 1. What is n? That is 1.073 minus 1. After solve this on calculator, you will get work input value, that is 21,929 joule. Divide with 1000 to convert into kilojoule, and it will give you 21.93 kilojoule. Next, we need to calculate the heat input or rejection that is required. First, we need to find the internal energy at the initial state, that is equal to H1 minus P1 V1. H1 value is 292.9 minus P1, that is 2.62. This terms in kilo, so you will also convert this into kilo. Just divide with 1000. After solving this, you will get the internal energy U1 value, that is 273.07 kilojoule per kg. Similarly, the U2 value is equal to H2 minus P2 V2. What is H2 value? This is H2, 322.6 minus P2, that is 8.2, multiply 10 to the power 5, multiply V2, that is 0.02615, and it will give you U2 value, that is 301.16 kilojoule per kg. Now from first law of thermodynamics, Q plus W is equal to change in internal energy. Then the value of Q is equal to change in internal energy minus W, and this change in internal energy is equal to U2 minus U1 minus the value of W. So what is U2? That is 301.16 minus U1 value, that is 273, minus the value of W, that is 21.93. After solving this on calculators, you will get the final Q value, and this is 6.16 kilojoule per kg. This is positive. This means that heat is supplied during this process, and this is our final answer. I hope you understand. If still there is any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.